School's pre-doctoral engagement series. We are glad to have you all here today. Before we begin, a quick note on the format. Each speaker will have 15 minutes for their presentation, followed by a 5-minute Q&A. The moderators will indicate when 3 minutes remain, so the speakers are requested to conclude within the allotted time to ensure that the session runs smoothly. So we'll start the session with our first speaker, Ankita Koley. She's a PhD student at the Department of Electronic System Engineering, IISc. She obtained her BTech in Electrical Engineering from the National Institute of Technology, Durgapur in 2018. Prior to joining IISc, she was a commercial executive at CESC from 2018 to 2020. Her research interests include communication networks, edge caching, edge computing, and optimization. She's currently working on caching and delivery of dynamic content. So you can start, Ankita.
Okay. Thank you, Kiran. Good evening, everyone. So in this presentation, I'm going to discuss what do you mean by caching of dynamic contents, the applications, the challenges, and the problems that that I have been solving in my PhD for my PhD thesis, and what are the future direction in this work. So consider a user is asking for a content which is far from it in a central server. Now, when the user is asking for the content, of course, it will be served to this user so by fetching from the far away server. After fetching, there could be two scenarios. One where it decides, okay, we can save it in its nearby server, or we don't save it, we just discard it. Now, in future, if there are several requests for the same content, if we saved it earlier, we could, save fetching from the server every time. Okay. So this phenomena of saving the content in a nearby server, a copy of a content in the nearby server is called caching. And the caching is done by content distribution networks. And why do we do caching? Because we want to reduce the response time of the users. So we don't want to fetch the content from a far server. It will incur delays, and it will also incur the congestion in the backbone. So the content distribution networks deploy caches in users' proximity to reduce the response time and improve the congestion in the backbone networks. Now, what are dynamic contents? Dynamic contents are those which get updated in real time. For example, if you consider Facebook's newsfeed or YouTube's recommendation page, these contents get updated accordingly users' engagements and users' preferences. And nowadays, most of the web applications use dynamic contents to improve user engagements. Now, let us consider a particular cache, say this cache, which is connected to the cloud server via internet. Okay. Now, here we have the dynamic contents which get updated. We assume that server has everything. So the contents get updated and it has the most updated version. Now, when the contents get updated here, the copy of the contents which were already in the cache gets outdated. Now, the users which are using these dynamic applications, they are interested in the most fresh version of these contents. So every time when user asks a content, if the edge cache, in order to serve the fresh version, edge cache fetch all the time, every time, then of course, again, the same problem happens that it has to, there will be huge delay and congestion in the backbone network. But if it serves the locally cached version, then it could potentially end up serving the stale version, which will affect the quality of experience of the user. So we aim to design caching policies which will, kind of balance the high latency for fetching the content from the server and serving potentially stale version that could affect the quality of experience of the users. Now, let us consider a scenario where there is a request by user to the local cache and it first look at its own cache whether it has the copy or not. Here in this case, it has its local copy and there is another version which is updated already. There have been updated in the central server. Now it can decide which one to serve. Either it can serve the stale information or it can fetch it from the far server and serve it. Okay. After serving, of course, it will replace the local copy. Let us consider another scenario where it is not in the cache. So it will definitely fetch the fresh version. After fetching, it has to decide whether it wants to save it or not, because it has limited cache capacity. And suppose the cache is already full. So if it wants to save it, it has to replace one content and which content it wants to replace. Now, here is the catch that the local cache does not know how many updates are happening at the central server. It has no knowledge of the central server until it fetches a content. Okay, so these are the challenges we face while we do dynamic caching, that it does not know the number of updates, it does not know which content is going to be requested, and of course it has limited capacity. Now, to this direction, we formulate a mathematical abstraction of this caching problem, and we consider a set of contents that is fixed and cache size that is also fixed and which is much lesser than the number of contents. And there is a request process. So we consider here Poisson process, and the request process is not identical for all the contents. Some contents may have higher demand, some contents may have lower demands. And how do we capture it? We capture it by the probability of requesting that particular content. For example, if you see here, the user demand, we call it a popularity distribution. So if you see these are the contents 1, 2, 3, 4, we index these contents. Now, if we see that the content 1 has higher chance of requesting more than other contents like 2, 3, 4 and so on. Similarly, content 2 also has higher chance of requesting than 3, 4, 5 and so on, but it has lower chance of requesting than content 1. So we can design the popularity depending upon the user demand. Now let us see how do we formulate the problem. Okay, so again, we consider a scenario where the requested content is cached and you serve the cached copy, the stale version. Then you pay an aging cost. If you fetch it, you pay a fetching cost. And of course, after fetching, you replace the fresh copy because the content, another copy was already there. So you don't have to take any caching decision. But in the other scenario where the requested content is not cached, you have to fetch it. Now, after fetching, if you decide, okay, I don't want to save it, then the configuration, what was the cache configuration, that remains same. Basically, you keep the other contents that were already cached. But if you decide to fetch and cache it, you have to decide which content you want to evict. Okay. Now, here our goal is to minimize the averaged over time, subject to this cache capacity constraint. Now, towards this goal, we propose a policy. It's called Whittle index-based policy. So what it does, it assigns each content a number depending upon its state. Now, what is a content state? A state is like it will have it will represent these quantities, whether it is cached or not. If it is cached, for how long it is cached, whether the content is requested or not. So these components will define the state of the content, and Whittle index-based policy will assign a number to these contents depending upon its state. Now let us see the index-based policy. Okay, suppose a content is requested. Now, okay, if it is in the cache, you see for how long it is in the cache. If it is beyond some threshold, then it is really old and you don't want to use it, you fetch it. After fetching, you replace the local copy. If it is below some threshold, you serve the cached copy. Okay, it is safe to serve a little bit older copy. Okay, but if it is not in the cache, then you fetch the requested content. After fetching, you compute the Whittle indices of the requested content and the contents that were already cached. Now you evict the content which has the least index. Okay, suppose this content has the minimum index. Now we can replace this content with this, the newly fetched content. Okay, this is the Whittle index based policy, and why we use Whittle index based policy. Okay, first thing is that it is very easy to implement. You just assign a number, you know the function, you just compute the Whittle indices from that function, and you assign a number in the content, and then you compare that number. Okay, secondly is it's a very low complex algorithm. It's increases only linear in number of contents, and it has been shown that in multiple works that it performs very close to optimal to the very close to optimal policy under some technical conditions. Okay, now let us see whether it is really, whether it does really perform good or not. So here, if you see the blue dotted line, it's the lower bound of the performance of our objective, and the orange line is our the cost of our policy. Okay, now if you observe, those coincides. So if our if the cost of our proposed policy coincides with the lower bound, that means this performs very close to optimal. And the purple one is to compare with the state of the art policies. The same problem has been studied by these people, and they have suggested some periodic periodic update policy. Of course, our policy performs better, much better than this. Now so this is one mathematical abstraction, and of course we have we have not considered everything. For example, if there is a, in general case, there is an wireless channel between the edge cache and the users. So if the transmission fails, what happens? You fetch a content or you serve the local copy, that time transmission fails. So we introduce another cost, which is called missing cost, when there is a failed transmission. And we design the channel, success rate with the probability. So with some probability, the content reaches the user. Okay. Here, what happens? You can attempt to serve a cached copy. If it fails, you pay missing cost. You can fetch and serve. Okay, and again, there will be a fetching cost when you are going to fetch. But if while serving, if the channel fails, you pay missing cost. And again, the objective is the same. You want to minimize the average cost subject to cache capacity constraint. Okay, let us consider another scenario where we don't assume any failure here in between edge cache and the users, but the edge cache and the internet, those are connected via wireless link, and this could happen in scenarios where you have micro base stations and macro base station, where the cache is at the micro base station, and those two base stations are connected via wireless channel. Okay. Now again, we design missing cost and success probability. Now what happens? You can serve the cache copy. Okay, there is no failure, so there is no problem. But and there is aging cost. But when you try to fetch and serve, you pay fetching cost. But suppose suppose there is a failure. Okay, then what will do? Then if the content is there, you can serve the cached copy. Again, there will be additional aging cost. Or if the content is there or not there, in any either case, you can deny service. Okay, so there will be a missing cost. In some cases, if the fetching cost is so high than the missing cost, you may want to deny fetch and serve. You just deny service and you can pay the missing cost. Okay. Now again, we propose here Whittle index based policy, and then our goal is to minimize the average cost subject to the cache capacity constraint. Okay. There is another extension which is very interesting, is that you let the request wait. There is no failure here or here, but you let the request wait for some time until you accumulate enough requests to fetch. Okay, so let us consider that scenario. Now suppose there is a request, you make it wait, another request, you make it wait, and so on. Then after enough number of requests get accumulated, you fetch and serve all the requests. Okay, and it will give you a queuing of all the contents. Okay, whenever you serve the content, you serve all the request that has been queued for that particular content. So for this queuing, for this waiting, there is a waiting cost per unit time. And when you serve the cached copy, there is only aging cost because you serve all the copies at all the contents at the same time. What I mean is that all the contents is that all the request for a particular content, not all the contents. Okay, and you can fetch and serve similar to there will be fetching cost. Again, our goal is to minimize the average cost subject to the cache capacity constraint. So in all these cases, we propose Whittle index-based policy, and there are different technicalities associated with it. Now we extend this to a network, and here we consider a simple network, which is a hierarchical network. Okay, so whenever users request it, it requests to one cache. If it has, it will serve. Otherwise, it will forward to the upper level caches. Okay, and if nothing is found in any of the caches, it can serve from the central. It can fetch from the central server and again transmit to the users via the downstream caches. Now here we consider we don't consider aging cost, but we consider dynamic contents, and we we design its usefulness via this, that any content in the cache is useful for a certain duration of time. So after some time, the content becomes useless. Okay, and it depends on the contents. For each content, there is a fixed interval for which it remains useful. So now, if there is a request and if the content is cached and useful, then only it can serve. Okay, otherwise it will forward to the next cache, and again, if the condition satisfies in the next cache, it will send it back to the users via the downstream cache. But now there is a transmission cost associated with this forwarding. Okay, and the same thing happens in the upstream caches. And again, if it is not found in any of the caches or neither useful, then it fetches from the server, and then you pay a fetching cost, which is usually more than the transmission cost in between the caches. Okay, now when a fresh content is fetched, where to cache the content? Okay, now there are two scenarios where one is that the content is not in the not found in the cache. Okay, then after fetching, you have to decide which cache you choose and which content from the cache you want to evict. There is another scenario where you have the content but it is not useful anywhere. Okay, then also you have to fetch and decide which cache you want to cache you want to choose. Because suppose you had the content here and it is not useful. Now when you fetch it, you may not want to save it here. You may want to save in the closer to the users. Okay, so here are the decisions, and again we want to minimize the average cost. And also the important thing is here is that one cache cannot know the statistics of all the caches. So we have to find some way to implement distributed caching. We cannot give it's not practically possible to share all the information of all the caches to one cache. Okay, so how to implement distributed caching? Okay, so again here we use Whittle index-based policies. Okay, now instead of one index, you will have multiple index corresponding to multiple caches, and our policy is to maximize the sum of indices across all caches. Okay, so I'll summarize that first we consider a simple problem, and then we extend it to the wireless channel between cache and users, then wireless channel between server and the local cache, then we allow it to be queued, and then we extend it to the tandem cache network. Now, in practice, we don't know the arrival rate or the update rate or the demand of the users. Okay, now what do we do in those cases, right? So in case of unknown arrival and update rate, there comes the reinforcement learning based policies. And this in this context, the reinforcement learning based policies are not studied. So this is an open area. Secondly, you don't want to confine yourself only in the tandem cache network. You want to go bigger, like for general cache network, where a general graph or a tree-like structure. In a general graph, it could be like request can arrive at any cache, not only the edge cache, which is which was the case in case of tandem network. In tree-like structure, the request arrives at the leaf caches and then it get forwarded to upstream cache in a hierarchical manner. So these are the open problems in this domain. And that's all I have. And this is my email ID. You can reach me anytime if you have any questions about my work. Thank you.
Thank you, Ankita, for the wonderful presentation. Are there any questions from the audience?
So I have one question. So normally, index arises when there is a hard constraint which is there in the problem and you relax it. So here, what was the hard constraint that you relaxed?
Okay, so here the hard constraint is that, okay, so here hard constraint is the cache capacity constraint, where you have to, every time you have to, you can cache this many contents, okay? But when we relax it, we just make it, so we relaxed it in such a way that on an average, you cache this many contents.
Right. So, but it may happen that actually, because of the policy, the number of contents stored can increase beyond 10. That can happen.
That can happen in the relaxed problem. Yes, that can happen in the relaxed problem, but not in the Whittle index-based policy.
No, but in the full index-based policy, finally, no, but since you're not dealing with the hard constraint, can't it happen that the number of entries cache goes beyond them?
Okay, so I understand. So the Whittle index computation depends upon the relaxed problem, but
Yes.
when we actually implement the Whittle index based policy, we choose the top M indices. So we always satisfy the hard constraint.
All right, thank you.
Ankita, we have one more question. How many flows were considered? Also, was the network congestion considered?
Okay, so the first question, flows in which problem? Flows if in the network, tandem cache network, or
Maybe you could answer both if there are more than two.
okay, so first question, I want some clarification on the first question. That can you please repeat once more?
It's basically how many flows or users were considered.
Okay. So here there are the requests are based on the contents, not so we have a set of users, and the requests for each content has been considered. So the number of flows is the number of contents. And the second question?
Was network congestion considered?
Okay, so so the network congestion is captured via the fetching cost. So the fetching cost can be both accounted for high latency, content acquiring cost, and the network congestion. So you want to put a, if you want much lesser congestion, you put a higher fetching cost. So this is how we captured it.
And there's one more question. Probably will the CDN topology play a role? Will it play a role in this?
Okay. So from the topological point of view, okay, in most of the problems we consider a single cache. I mean, we focused on the single cache that you have the you just decide whether you want to cache or not a content, how long you want to keep there. Now, when you talk about topology, so basically we just considered the hierarchical nature of the CDN. That in CDN, what happens if you don't get a content from the lower level cache, you go to the upstream caches. But CDN topology is much complex that I have been discussing in that the future work. It could be a general graph. It does not have to be a tandem network structure, and it could be a tree-like structure. So we did not capture the full topology. We could capture some of it.
Okay, thank you, Ankita.
Thank you so much for listening. Have a nice day.